Welcome to Universe Orbit, your gateway to exploring the vast wonders of space, where the mysteries of the cosmos unfold through captivating videos. Don't forget to subscribe so you never miss a single voyage through the infinite universe. Magnetic fields are invisible architects of motion and structure across the cosmos, whispering directions to charged particles, sculpting the shapes of stellar winds, and shielding planets from the raw fury of their parent stars. Where gravity draws matter together, magnetism often decides how that matter moves once it is ionized, guiding flows of plasma along invisible field lines and, at times, breaking its own rules in sudden, explosive rearrangements. Space weather, the daily and episodic changes in the near-space environment, driven chiefly by the magnetic activity of the sun and its interaction with planetary magnetic shields and atmospheres, is the practical, urgent face of these magnetic processes. It is a phenomenon that links the deep physics of magnetic fields and plasmas to human technologies and the future of exploration, turning abstract concepts into auroral curtains, disrupted satellites, and decisions about how to keep astronauts and infrastructure safe beyond Earth. To understand how magnetic fields shape space weather, it helps to begin with the most basic property of magnetism in astrophysical settings, its intimate relationship with charged particles. In ordinary materials on Earth, magnetic fields arise from the alignment of atomic-scale magnetic moments and the motion of electrons. In the hot, diffuse environments of space, stellar atmospheres, planetary magnetospheres, in the tenuous interplanetary medium, the dominant actors are plasmas, gases so hot that atoms lose electrons and become electrically charged. In a plasma, magnetic fields and plasma flows are coupled through the rules of magnetohydrodynamics. Field lines act like springs or tracks. Particles gyrate around them, move along them, and when conditions change, can cause the field lines to bend, twist, and even reconnect. The language of magnetism in space thus becomes the language of fields, currents, waves, and instabilities, all mediated by the fluid-like behavior of plasma. The sun is the primary source of the space weather that matters to Earth and its neighborhood. Deep within the solar interior, convective motions and differential rotations stretch and wind magnetic fields into complex configurations. Over decades and centuries of observation, it became clear that the sun's magnetic activity waxes and wanes in a roughly 11-year rhythm, a solar cycle that governs the number and intensity of sunspots, flares, and the eruptions known as coronal mass ejections. Sunspots are regions of concentrated magnetic flux piercing the solar surface. They serve as the staging grounds for dramatic magnetic rearrangements. When magnetic fields that have been twisted and stressed by motion in the solar plasma suddenly reconnect, the stored magnetic energy converts quickly into heat, light, and kinetic energy. That process powers solar flares, bursts of electromagnetic radiation across the spectrum, and sometimes propels enormous bubbles of magnetized plasma outward as coronal mass ejections. Coronal mass ejections, or CMEs, are among the most consequential drivers of space weather. A single CME can expel 1 billion tons or more of plasma into the heliosphere, carrying with it a magnetic field that is often twisted like a rope. If this magnetized cloud collides with the Earth's magnetic environment, it can strongly disturb the magnetosphere, compressing it on the day side and injecting energy and particles into the magnetospheric system. The consequences range from splendid to serious: intense auroral displays at lower latitudes, induced currents in power grids, satellite anomalies, and increased radiation exposure for high-altitude flights and spacecraft. The severity of the interaction depends crucially on the orientation of the magnetic field embedded in the CME relative to Earth's field. When the CME's magnetic field points opposite to Earth's, known as a southward orientation in Earth's local coordinate system, the fields can readily reconnect at the dayside magnetopause, opening a door through which solar energy and particles flow into the near-Earth environment. The steady, less dramatic stream of particles and magnetic field that fills the space between the sun and the planets is the solar wind, born from the million-degree corona and accelerated into a supersonic breeze. The solar wind's speed and density vary with solar activity, and the structure of the solar corona. Fast solar wind streams often emerge from long-lived coronal holes, regions of open magnetic field where plasma flows outward unobstructed. The interaction between high-speed streams and slower ambient wind can form co-rotating interaction regions, which are persistent structures that can buffet the magnetosphere regularly as the sun rotates. Embedded within the wind are magnetic field lines dragged out from the sun to form the Archimedean spiral, a pattern created by the combination of radial outflow and solar rotation. The Parker spiral determines the large-scale connectivity between the sun and distant points. It helps explain why eruptions and energetic particles from certain solar longitudes can reach Earth with greater effectiveness than others. Magnetospheres are the protective magnetic bubbles carved out by intrinsic magnetic fields around planets. Earth's magnetosphere begins where the pressure of the planetary magnetic field balances the dynamic pressure of the incoming solar wind. The day-side magnetopause, the boundary between magnetosphere and solar wind, is a dynamic interface where reconnection, boundary waves, and plasma entry occur. On the night side, the magnetosphere stretches into a long magnetotail, a repository for magnetic energy that can be released explosively through reconnection to power substorms. Sudden injections of energized particles into the near-Earth region that feed bright auroral displays. Other planets have magnetospheres shaped by the strength and geometry of their internal fields and by their atmospheric and plasma environments. Jupiter's magnetosphere, inflated by its strong field and fast rotation, is vast and driven partly by internal processes such as volcanic outgassing from its moon Io, which injects material that becomes ionized and populates the Jovian magnetosphere. Mars, with a weak and patchy crustal magnetization instead of a global dipole, interacts with the solar wind in a more direct way, allowing atmospheric escape to be enhanced under certain conditions and illustrating how magnetism, or the lack of a global shielding field, influences a planet's long-term atmospheric evolution. Magnetic reconnection deserves special attention because it lies at the heart of many abrupt space weather events. The concept is simple in words, but complex and rich in physics. Two oppositely directed magnetic field lines brought together in a conducting plasma can change their connectivity, breaking and rejoining to form new configurations. In the process, the magnetic energy converts into particle kinetic energy and heat. Reconnection occurs in thin current sheets and can lead to jets, particle acceleration, and explosive releases such as solar flares and fast, narrow outflows in planetary magnetotails. Reconnection is inherently a multi-scale process. Kinetic plasma physics at microscopic scales sets the rate at which it occurs, while macroscopic magnetic topology dictates where and when energy accumulates. Understanding reconnection has practical implications because it helps predict when and how magnetic energy stored in the corona or magnetotail will be unleashed. Energetic particles, electrons and ions, accelerated to high energies, are among the most hazardous products of magnetic activity. Solar energetic particles produced by powerful flares or by shock waves driven by fast CMEs can reach near relativistic speeds and penetrate spacecraft shielding, damaging electronics and posing a radiation hazard to astronauts. They also affect the ionosphere, enhancing ionization and sometimes causing radio blackouts that disrupt high-frequency communication and navigation signals. Within planetary magnetospheres, energetic particles can be trapped and form radiation belts. Earth's Van Allen belts are dynamic. Their population and energy spectra change in response to geomagnetic storms and wave-particle interactions. Satellite operators must consider radiation belt environments when planning orbits and designing hardened electronics to ensure longevity and functionality. The ionosphere and thermosphere, the upper layers of Earth's atmosphere, are strongly influenced by magnetic and space weather activity. When solar extreme ultraviolet and X-ray radiation intensifies during flares, the ionosphere's electron density can increase rapidly, disrupting radio wave propagation and GPS signals. During geomagnetic storms, enhanced currents and precipitating particles heat the upper atmosphere, causing it to expand. Increased atmospheric drag can lower satellite orbits, shortening their operational lives or changing their trajectories enough to require orbit corrections. Electric currents flowing in the ionosphere and magnetosphere close through the ground, inducing quasi-DC currents in long conductors such as pipelines and power grids. These geomagnetically induced currents can overload transformers and lead to blackouts, as dramatic historical events have shown. Thus, small-scale physics, particles guided by magnetic fields, scales up to generate tangible technological impacts on the ground. Observing and predicting space weather is an active, multidisciplinary enterprise. Spaceborne observatories provide frontline information. Solar imagers and coronagraphs reveal the birth and trajectory of CMEs. Spacecraft stationed at the Lagrange point OL. One detect the solar wind and interplanetary magnetic field before they reach Earth, giving crucial lead time. In situ measurements from satellites in the magnetosphere characterize particle populations and field configurations. Ground-based magnetometers map the global currents flowing in response to space weather disturbances. Models range from empirical forecasts based on statistical patterns to physics-based simulations that couple the solar corona, heliosphere, magnetosphere, and ionosphere. Forecasting space weather remains challenging because many critical processes are nonlinear, multi-scale, and often unpredictable in their timing and magnitude. Nevertheless, improvements in observations, data assimilation, and computational power have bolstered forecasting skill, enabling better warnings for satellite operators, power grid managers, and human spaceflight planners. The Sun is not the only star that matters to the magnetic and atmospheric fates of planets. Exoplanetary science has thrust magnetic fields into a new role as a potential factor in habitability. A strong planetary magnetic field could shield an atmosphere from erosion by stellar winds, while magnetic interactions between star and planet can generate additional heating or even observable emissions. The detection of magnetic fields on exoplanets is at the frontier of current capabilities, often inferred indirectly through radio emissions or star-planet interaction signatures. Likewise, the magnetospheres of giant planets around other stars could shape their moon's environments, influence atmospheric chemistry, and affect potential biospheres. Investigating magnetic fields beyond the solar system extends the relevance of space weather. It asks whether magnetic shielding is a prerequisite for long-lived, life-friendly atmospheres, and how stellar magnetic variability sculpts planetary climates over geological timescales. Space weather is also a design parameter for engineering in space. Satellite buses, mission planning, and human exploration architectures must incorporate the realities of magnetically driven phenomena. Shielding against energetic particles adds mass and cost, while system redundancy and fault-tolerant electronics mitigate single-event upsets caused by energetic particles. Timing of sensitive operations such as satellite deployments and extravehicular activities for astronauts often depends on space weather forecasts. For interplanetary missions that venture outside Earth's protective magnetosphere, exposure to solar energetic particles and galactic cosmic rays becomes a principal risk. Planetary protection and habitat design for long-duration missions must consider both the typical background radiation and the episodic spikes produced by solar eruptions. Even for aviation, space weather planning has practical consequences. Polar flights may be rerouted during severe solar events to avoid communication blackouts and increase radiation doses. Beyond technological concerns, the study of magnetic fields in space is a journey into fundamental physics. Magnetohydrodynamics provides a framework for much of the macroscopic behavior, but many salient processes require kinetic plasma physics, where individual particle motions and wave-particle interactions matter. Turbulence in magnetized plasmas remains a deep puzzle. How energy cascades from large scales where it is injected by solar or planetary motions, down to small scales where dissipation, heating, and particle acceleration occur. This cascade shapes the heating of the corona, the transport of energetic particles, and the dissipation of magnetic energy in magnetospheres. Observations from multi-spacecraft missions that can sample different points in space simultaneously, such as clusters of satellites flying in formation, have been transformative in unraveling these processes. They provide spatial context that single-point measurements cannot, offering clues to the three-dimensional geometry and dynamics of magnetic structures. History is peppered with notable episodes that underscore the societal importance of magnetic activity in space. The Carrington event of 1859, a powerful solar storm observed as intense auroras at low latitudes and dramatic telegraph system failures, stands as a cautionary tale. Were a similar event to hit today, the impact on interconnected power systems, satellites, and communications could be immense. Modern life's reliance on space-based services magnifies vulnerability. Locating resilience in systems and preparing coordinated responses are active priorities for governments and industries. International cooperation for space weather monitoring and information sharing has grown in recognition that these are global hazards not confined by national borders. The interaction between magnetic fields and atmospheres is not only a hazard, but a creative force shaping planetary evolution. Magnetic shielding helps retain atmospheres against stellar stripping, but magnetic fields can also provide pathways for atmospheric escape under special conditions, such as when reconnection opens channels through which ionized particles can stream away. On early Earth, magnetic activity likely played a role in protecting a young, perhaps volatile atmosphere, while facilitating chemical pathways for prebiotic chemistry via energetic particle precipitation. For Mars, the loss of a global magnetic field likely accelerated atmospheric erosion by the solar wind, contributing to the cold, thin atmosphere we see today. Understanding these magnetic and atmospheric couplings is essential for reconstructing planetary histories and assessing the long-term habitability of worlds. Instruments and techniques for probing magnetic fields in space are diverse and ingenious. Direct measurements using magnetometers on spacecraft provide local field vectors, while remote sensing, imaging of polarized light, radio emissions, and spectral diagnostics can infer magnetic fields in regions where direct sampling is impossible. On the Sun, vector magnetograms map the photospheric field, while coronal seismology and Faraday rotation of radio waves offer windows into the corona's elusive magnetic structure. During planetary encounters, magnetometers and charged particle detectors work in concert to paint a picture of the field and plasma environment. Laboratory experiments and numerical simulations complement observations, enabling controlled tests of theories about reconnection, turbulence, and wave-particle interactions. Together, these tools have built a layered understanding of how magnetic fields operate from the smallest kinetic scales up to the architecture of entire magnetospheres. Predicting the specifics of space weather remains an imperfect science because of the complexity and sensitivity of the processes involved. Small changes in magnetic topology or local plasma conditions can determine whether a stressed solar field gently relaxes or violently erupts. Forecast models try to capture these dynamics with varying degrees of fidelity. Empirical models distilled from decades of observation provide useful, computationally inexpensive guidance and are often used operationally. Physics-based models such as magnetohydrodynamic simulations of the corona and heliosphere, coupled with magnetospheric ionospheric models, aim to capture causal mechanisms and provide more physically motivated predictions. Advances in data assimilation, melding observations with models in real time, are promising, but the heterogeneity and incompleteness of observations remain hurdles. Despite these challenges, operational forecasting services now provide actionable warnings that reduce risks and inform mitigation strategies. There is an aesthetic side to magnetic phenomena as well. Auroras are magnetic weather made visible. The shimmering curtains and dynamic arcs that light polar skies are the sky's response to particles guided along field lines and accelerated into the upper atmosphere, where they collide with atoms and molecules to create glowing displays. Auroras are a reminder that magnetic fields channel invisible energy into radiant living forms. They are also natural laboratories because the shapes, motions, and spectra of auroras encode information about the precipitating particles, the accelerating mechanisms, and the magnetospheric dynamics that produce them. A future where human activity spreads more broadly through the solar system will require a deep operational understanding of magnetic interactions in space weathers. Lunar and Martian missions will be sensitive to energetic particles and atmospheric responses. Designing habitats, habitats, trajectories, and operational timelines will depend on reliable space weather information. The need for resilient satellite architectures and distributed observational networks will increase as more nations and commercial actors launch constellations for communications, navigation, Earth observation, and deep space infrastructure. Investing in diverse observing systems, including solar imagers, heliospheric monitors, and planetary probes, coupled with robust modeling frameworks and international data sharing, will be essential to manage space weather risks and unlock new opportunities. Fundamentally, the story of magnetic fields and space weather is a story of coupling. The coupling of microphysics to macroscopic structures, of a star to its planets, of explosive dynamics to slow evolutionary trends, of scientific curiosity to pragmatic engineering. It is a field where basic research, probing how reconnection accelerates particles or how turbulence dissipates energy, directly feeds operational outcomes such as improved forecasting and mitigation. The duality of beauty and hazard, so evident in auroras and geomagnetic storms, invites both awe and respect. As we imagine a future where societies are even more entwined with technologies that depend on space, our capacity to read and respond to magnetic weather will matter more. The invisible lines that guide particles and shape plasmas are, in that sense, also the lines that bind modern civilization to the larger cosmic environment. The magnetic universe stretches beyond human scales into the domains of galaxies and galaxy clusters, where fields influence star formation, cosmic ray transport, and the dynamics of interstellar gas. In those realms, space weather takes different forms: galactic winds and magnetized shocks that regulate the life cycle of gas and stars. Yet the same underlying physics, charged particles interacting with fields, instabilities and reconnection, turbulence across scales, repeats itself. This universality is humbling. By studying magnetic processes in our neighborhood, from the twisting of solar coronal loops to the bending of field lines in Earth's magnetotail, we learn principles that have echoes across the cosmos. Practical steps to mitigate space weather impacts rely on a blend of technology, policy, and preparedness. For critical infrastructures, improving resilience means hardening hardware, diversifying communication paths, and designing grid systems to tolerate quasi-DC currents induced during storms. For space missions, it involves radiation-hardened electronics, redundant systems, and operational protocols that delay vulnerable operations during high-risk periods. For society at large, clear communication channels between scientific centers, operators, and policymakers reduce confusion during events. International collaboration is particularly important because space weather does not respect borders. Global monitoring networks and shared forecasts are more than science. They are public goods that protect a globally interconnected modern world. Research frontiers in magnetic and space weather science are vibrant. They include gaining a predictive understanding of coronal mass ejection initiation, quantifying particle acceleration at shocks and reconnection sites, unraveling the turbulence cascade in magnetized plasmas, and constraining magnetic influences on atmospheric escape on diverse planetary bodies. New missions, novel instrumentation, and improved numerical techniques are converging to tackle these questions. Artificial intelligence and machine learning are being integrated into forecasting pipelines, helping to detect subtle precursors to eruptions in vast solar datasets and to optimize model parameterizations. Meanwhile, multi-messenger approaches that combine electromagnetic observations with in-situ measurements and theoretical models are delivering richer, more cohesive pictures of magnetic phenomena. Education and public engagement matter too, because the implications of magnetic space weather touch daily life in subtle ways. Navigation signals we take for granted, satellite-based finance systems, and the streaming of information across the globe can all be affected by magnetic storms. The wonder of auroras and the palpable drama of satellite maneuvers during storms offer hooks to engage learners about plasma physics, magnetism, and the interface between the sun and Earth. Accessible narratives that connect the physics to tangible outcomes foster a scientifically literate public better equipped to support and benefit from space weather preparedness. Stepping back, the interplay of magnetic fields and space weather offers both a challenge and an opportunity. It challenges our ability to predict complex, nonlinear systems and to design resilient technologies in the face of natural variability. It offers opportunities to deepen our understanding of fundamental plasma processes, to protect and optimize vital infrastructures, and to expand human presence into space with safety and foresight. Magnetic fields are silent sculptors, shaping the motion of particles and the destiny of atmospheres. The weather they create is a reminder that the cosmos is dynamic, interactive, and intimately connected to our technological civilization. As humanity moves further into space, we will increasingly rely on a tapestry of observations, models, and policies to read magnetic signs and to respond effectively. This tapestry will be woven from the threads of fundamental research and practical engineering, of international cooperation and informed public policy. In the meantime, the next aurora that paints the night sky is both a spectacle and a message. The sun and magnetic fields are active participants in our planetary story, making the heavens both a laboratory and a hazard to be respected. Understanding magnetic fields and space weather is not an esoteric pursuit. It is a necessary chapter in the broader narrative of life and technology in a magnetic universe, where invisible forces ripple across space and time, connecting the smallest particle gyrations to the grand sweep of planetary and stellar evolution. The future of our understanding is not limited to observation and modeling. We are now entering an era where humanity can manipulate and explore magnetic environments more directly. Concepts for artificial magnetospheres have been proposed as protective shields for spacecraft or even entire planets such as Mars. By generating a controlled magnetic field, a spacecraft could deflect charged particles and reduce radiation exposure without relying solely on heavy material shielding. For Mars, which lacks a global field, researchers have investigated whether a magnetic dipole placed at a strategic point, like the Mars-Sun L1 location, could expand into a protective bubble large enough to lessen atmospheric loss and create a safer radiation environment for future colonists. While these ideas remain speculative and technologically challenging, they highlight how magnetic science may evolve from passive understanding to active engineering of space weather conditions. Human exploration missions provide compelling motivation for mastering space weather. On the moon, astronauts do not enjoy the protection of a thick atmosphere or a global magnetic field. Solar energetic particle events could deliver radiation doses sufficient to threaten human health with little warning. Understanding the timing and severity of these events is crucial for mission planning. Crews will need access to shelter, storm forecasting, and real-time alerts that allow them to halt extravehicular activity during dangerous conditions. On Mars, the thin atmosphere offers some shielding for the surface, but exposure remains significantly higher than on Earth. The planet's patchy crustal magnetic regions provide localized mini-magnetospheres, which might one day be used strategically when selecting base sites or designing infrastructure placement to take advantage of small pockets of enhanced protection. The links between magnetic fields and habitability extend deeply into astrobiology. Magnetic protection could influence not only whether a planet retains air, but also how chemistry unfolds at the boundaries between atmosphere and space. Energetic particles precipitating along field lines can create nitrates, hydrogen oxides, and other chemically active species that may have played roles in prebiotic chemistry on early Earth. In regions like Jupiter's moon Europa or Saturn's moon Enceladus, interactions between magnetospheric particles and surface ice produce radiolytic chemistry that generates oxygen and complex molecules. These processes hint that magnetism may be part of the toolkit nature uses to drive complexity and energy flow in environments that are otherwise cold and dark. Such worlds remind us that space weather is not only a hazard, it can also be a source of energy and transformation. Understanding how magnetic fields evolve on planets is also essential for interpreting their distant past. The Earth's own magnetic field has reversed polarity numerous times over geological history, with north and south magnetic poles swapping locations. These reversals are recorded in volcanic rocks, where iron-bearing minerals align with the prevailing field as they cool, preserving a fossilized snapshot of magnetic direction. Reversals appear chaotic in timing, but reflect the fluid motions of the liquid outer core where Earth's field is generated by dynamo action. During reversals, field strength may weaken, potentially reducing shielding effectiveness temporarily. While such variations have not caused mass extinctions, they may have allowed increased radiation at the surface and accelerated evolutionary pressures. Magnetic history, therefore, is interwoven with biological history. Even within the Sun, magnetism plays a role more mysterious than we yet fully understand. The solar corona is dramatically hotter than the visible surface below, defying expectations from simple radiative heating. One leading explanation attributes this coronal heating to a constant ballet of small-scale magnetic reconnection, nanoflares, that release energy in countless tiny bursts, rather than occasional huge eruptions. If this interpretation proves correct, then the most significant contributor to space weather may not be the dramatic events we already track, but the subtle, persistent magnetic activity that energizes the solar atmosphere and drives the solar wind. Learning how these small features aggregate to influence large-scale space weather is one of the great puzzles of heliophysics. Magnetic fields also carry information. The structure and orientation of magnetic fields in a CME can reveal the forces that launched it and help forecast how it will interact with Earth. In situ measurements taken by spacecraft traversing such clouds help build three-dimensional reconstructions, similar to unwrapping a twisted, evolving rope. With enough observational coverage, magnetic footprints on the Sun can be algorithmically traced into the heliosphere, eventually forming predictive maps of magnetic connectivity between our star and various regions of space. Such mapping has profound implications. Astronauts could one day position spacecraft in areas magnetically well-connected to active regions to detect particle storms earlier, gaining precious extra minutes or hours of warning before dangerous radiation arrives. The story of magnetic fields is ultimately a story of energy transfer. Energy stored invisibly in field lines can burst into motion, heating Gauss-Samas, accelerating particles and triggering cascades of further changes. Waves travel along magnetized plasma in rich families. Alphin waves, magnetosonic waves, Whistler waves, each transporting momentum and energy differently. Wave-particle interactions govern how radiation belts grow and shrink, how auroras pulse and dance, and how turbulence shapes the transport of plasma throughout the heliosphere. These processes are not only scientifically fascinating, but decisive in determining the strength, scope, and consequences of space weather events. As we probe farther outward, interest grows in space weather analogs around other stars. Red dwarf stars, for instance, make up the majority of stars in our galaxy and are frequent hosts to planets in the so-called habitable zone. But many are extremely magnetically active, unleashing flares far more powerful relative to their size than the Sun ever produces. Planets around such stars may be bombarded with intense space weather, challenging their ability to maintain atmospheres or surface water. Habitability in those systems may hinge on how strong a planet's magnetic field is, or how its atmosphere responds to continuous particle blasting. Observations of stellar flares, combined with models of atmospheric escape, are beginning to answer whether magnetic storminess rules out life in many otherwise promising systems, or whether nature has developed robust protective adaptations that we have yet to discover. Space weather also serves as a bridge between near-Earth science and the broader physics of astrophysical plasmas. Magnetic reconnection is seen not only in the Sun's corona and Earth's magnetotail, but also inferred in distant environments such as pulsar magnetospheres, accretion disks around black holes, and jets launched from active galactic nuclei. In these extreme places, the same fundamental principles apply, but under conditions of relativistic particle speeds, enormous fields, and extreme gravity. By studying reconnection in accessible environments like the magnetosphere, we refine theories that may explain the astonishing energy outputs seen across the universe. Thus, every geomagnetic substorm is a local chapter in a universal story. The human experience of magnetism in space has grown more vivid through modern exploration. Astronauts on the International Space Station have watched auroras from above, seeing tendrils of green and red swirl beneath them as particles rush along field lines into the atmosphere. Crew members describe these views as among the most beautiful sights in orbit, a reminder of the living relationship between Earth and Sun. Meanwhile, satellites experience the harsher realities. Sudden voltage spikes from charged particle hits, electronics glitches, and orbital decays during geomagnetic storms. Designing spacecraft is therefore an exercise in balancing awe with caution. Large-scale infrastructure in space is similarly vulnerable. Global internet services increasingly rely on huge constellations of satellites in low Earth orbit. These orbits are most affected by atmospheric expansion during storms, leading to increased drag that can deorbit satellites prematurely unless operators respond quickly with orbital boosts. As constellations grow to tens of thousands of satellites, even moderate storms could create logistical challenges. Planning for space weather resilience becomes a matter of commercial strategy as much as scientific necessity. When powerful storms hit Earth, regions far from the magnetic poles can still feel the effects through power grid disturbances. Operators can temporarily reconfigure grid loads, reduce long-distance connections, or take critical transformers offline when strong storms are forecast. These decisions rely on timely alerts and accurate predictions. In the future, automated systems driven by real-time data and artificial intelligence may help shield critical infrastructure by reacting faster than humans can. Ultimately, forecasting space weather is not just a scientific triumph, it is a foundation for global safety. Public awareness of space weather is growing. Auroral tourism has boomed in regions like Scandinavia and Canada, with travelers eager to witness the magnetic sky dance. Media coverage of major solar eruptions brings attention to the science behind them. Schools incorporate lessons that connect Earth's magnetic environment with sustainability and technology. The more people understand how connected our lives are to magnetic events millions of kilometers away, the more support there will be for continued research and preparedness. Looking further ahead, technologies that directly harness magnetic field interactions may become practical. Electrodynamic tethers could provide drag or propulsion for satellites by exchanging momentum with Earth's magnetic field. Plasma shields might one day protect deep space vehicles from radiation more efficiently than current material methods. Even the dream of a fusion reactor, powered by magnetically confined plasma, relies on mastering the same physics that govern the sun itself. In this way, our progress in understanding space magnetism could power the next wave of civilization's growth. The more we learn, the more evident it becomes that magnetic fields connect everything. They channel the solar wind, shape planetary boundaries, influence radiation environments, and guide particles dancing in auroras. They also connect the laws of physics across huge scales, linking tiny particle spirals to vast cosmic currents. Magnetic fields are silent, invisible structure, and what we call space weather is simply their interaction made tangible. Energy released, particles accelerated, atmospheres disturbed. Yet despite their invisibility, magnetic fields have a personality. They store tension like stretched elastic bands. They twist, snap, and rearrange themselves in fleeting moments of explosive power. They create patterns in charged gas as intricate as any terrestrial weather system, complete with storms, waves, and seasons driven by the rhythms of the sun. They give planets character. Jupiter's enormous magnetosphere makes it a miniature solar system, while Mars's absence of a global field renders it vulnerable and exposed. Even Earth's protective shield is not static. It breathes and reshapes constantly in response to the solar wind, adapting moment to moment like a living system. Space weather, then, is not just a threat, but a sign of vitality. It shows that our star is active, dynamic, and still shaping the solar system millions of years after its birth. It reminds us that Earth is not isolated. It is plugged into a cosmic circuit, exchanging energy and information with the sun. And as humanity steps further into that circuit, sailing through magnetic seas, we must learn to navigate its storms wisely. The mission of understanding magnetic fields and space weather continues to expand as new spacecraft launch, new sensors come online, and new theories rise to meet the complexity of reality. Missions like Parker Solar Probe and Solar Orbiter are diving closer to the sun than any spacecraft before. sampling the birthplace of the solar wind and the crucible of coronal magnetism. Constellations of small satellites explore Earth's magnetosphere in growing detail, capturing reconnection on scales both tiny and vast. Ground-based telescopes and radio arrays observe the solar surface and atmosphere with unprecedented resolution, catching the subtle motions that foreshadow eruptions. Together, these tools form an evolving nervous system for our planetary society, sensing, analyzing, and ultimately predicting the mood of the magnetic star that sustains us. In each discovery lies a deeper appreciation of the balance between security and vulnerability. We are sheltered by Earth's magnetic cocoon, yet increasingly dependent on systems that lie outside it. We see beauty in auroras, yet recognize the danger in the storms that power them. We push farther from home, yet rely more heavily on constant awareness of magnetic influences. The future of space weather science will be to maintain that balance, to ensure that wonder and exploration flourish while risk is understood and reduced. In the grand tapestry of cosmic forces, magnetic fields are threads that hold structure together, while space weather is the visible tug and ripple of those threads when energy flows from one region to another. To study them is to study the heartbeat of our solar system, the pulses of a star that has given life to a world and now challenges its creations to adapt. We are only beginning to truly see the magnetic universe. As we refine our instruments, deepen our models, and extend our reach, we will uncover patterns that today remain invisible. One day, predicting a solar storm may be as routine as forecasting terrestrial weather. One day, spacecraft may surf magnetic currents as naturally as ships harness wind. One day, our descendants on Mars or moons beyond may look up at alien auroras, understanding them not with fear, but with informed respect. For now, every magnetic storm is a reminder. The sun speaks in the language of fields and plasma, and space weather is its voice. By listening closely, we learn not only how to protect ourselves, but how profoundly connected we are to the wider cosmos. The invisible lines that arc through space become visible in our knowledge, shaping a safer path for exploration and illuminating the dynamic beauty of a universe ruled by magnetism. The exploration of magnetic fields does not stop at our solar system. As astronomers gaze deeper into the Milky Way and beyond, we uncover magnetic influences everywhere, in the heart of galaxies, in the void between stars, and even stretching across the vast cosmic web that outlines the largest structures in the universe. Space weather, a phenomenon we first learned to fear because of its effects on Earth, may turn out to be a universal language spoken by stars and planets alike. By studying it, we gain a deeper understanding of how nature transfers energy, sculpts environments, and shapes the conditions necessary for habitability. Perhaps one day the ability to read this magnetic language will guide humanity safely as we journey across star systems. Our spacecraft serve not only as tools of observation, but also as pioneers navigating hazardous magnetic terrain. Missions like ESA's Solar Orbiter and NASA's Parker Solar Probe are humanity's first attempts to fly directly into the domain where the sun's magnetic power is born. These missions reveal a world of plasma streams, twisting rope-like magnetic flux tubes, and patches of the sun's atmosphere that fling outward like volcanic explosions. Each discovery teaches us not just how the sun creates solar wind, but also how magnetic tension can snap suddenly, unleashing storms that resonate across billions of kilometers. One key revelation is that the solar wind is not a uniform stream, but a chaotic river with fast and slow currents, turbulent whirlpools, and violent shocks. The structure of these flows depends heavily on whether the magnetic field lines they travel along are open or closed. The dance between magnetism and plasma is complex, but it is the key to predicting when space weather might grow dangerous. Imagine the future where we monitor space weather with the same precision that today we track hurricanes. A network of probes stationed around the sun could act like a cosmic early warning system. Data from these silent guardians could give us days or even weeks of notice before a potentially catastrophic solar storm reaches Earth. Power grids could switch into protective modes. Astronauts could shelter in safe areas of spacecraft, and airlines could reroute away from polar regions. Predictive space weather science is more than convenience. It may one day save global infrastructure from collapse. The risks will only increase as humanity expands into space. Low Earth orbit is becoming busier every year, filled with satellites that support navigation, finance, communication, and defense. A single major solar event could disable hundreds of them at once. Future lunar bases may need thick layers of regolith or electromagnetic shielding to protect crew from solar particle events. Missions to Mars, with months of exposure between planets, must account for radiation levels that fluctuate depending on the sun's moods. Even routine tasks like operating rovers on the Martian surface could be disrupted by magnetic disturbances that disrupt electronics or power generation. What about planets beyond our solar system? Astronomers have identified thousands of exoplanets and many orbit red dwarf stars, small, cool stars that are incredibly common in the Milky Way. Yet red dwarfs are notoriously magnetically active. They emit powerful flares and streams of charged particles that may constantly erode planetary atmospheres. A world might orbit in the habitable zone where liquid water is possible, but if its atmosphere is stripped away by fierce space weather, life may never gain a foothold. Understanding these relationships helps us refine our expectations about where to search for life and how to evaluate habitability. Magnetic fields, then, are guardians of habitability. They are also storytellers. Each planet's magnetic field encodes its internal structure, its age, and even its origin. As iron cores solidify or convect, as heat escapes, as tectonic or tidal forces shift, magnetic fields evolve. Some grow stronger, others decay. Mars once had a global magnetic field, strong enough to protect flowing rivers and perhaps ancient oceans. But as its internal dynamo faded, its atmosphere was left vulnerable, and space weather claimed it piece by piece. Earth, still warm inside, still churning with motion, still holds on to its shield. Our planet's magnetic heart allows our biosphere to remain stable and for life to flourish on land. As we progress in our exploration, we learn that magnetic fields are neither static nor eternal. They undergo cycles and reversals. The sun flips its polarity every 11 years, reshaping the entire heliosphere. Earth's field also reverses sporadically, sometimes staying stable for hundreds of thousands of years, and sometimes flipping more frequently. During these reversals, the field weakens, potentially allowing more cosmic radiation to reach the ground. Some researchers wonder if these episodes left imprints in the history of life, perhaps influencing mutation rates or causing climate shifts. We do not yet know the full consequences, but the connection between magnetism and life continues to deepen as new evidence emerges. Cosmic rays present another layer to the story. These high-energy travelers originate outside the solar system and are accelerated by powerful astrophysical engines, supernova explosions, pulsars, and the turbulent hearts of galaxies. They race across space at nearly the speed of light, and when they reach planets, magnetic fields are the first line of defense. Earth's magnetosphere funnels many cosmic rays toward the poles, where they produce auroras instead of bombarding the surface with harmful radiation. On worlds without magnetic shields, the surface becomes a battlefield where cosmic energy collides with atmospheres, chemistry, and potentially biology. By studying cosmic rays and how magnetic fields deflect them, scientists gain clues about whether a distant planet can remain safe for life. Even interstellar space, once thought to be calm and empty, hides magnetic structures that stretch light years across. The Milky Way's magnetic field shapes the flow of cosmic plasma and influences star formation. Magnetic filaments guide gas clouds, and magnetic turbulence can trigger or suppress the birth of stars. The cosmic web that links galaxies together may itself be laced with enormous magnetism, connecting clusters of matter through invisible threads. Space weather on a galactic scale may involve shock waves from colliding galaxies, massive jets from supermassive black holes, or waves from stellar nurseries expanding into the void. This growing picture suggests something profound. Magnetism is one of the universe's master architects. It is a force that does not just react to cosmic events, it helps define them. Space weather is not a localized quirk of our sun, but a sign of universal dynamics. Energy traveling along invisible rails, carrying information about the engines that drive stars, planets, and galaxies. Back on Earth, our awareness of space weather has become personal. Aurora hunters cheer when the sun grows active because it means the night sky may burst into color. But utilities engineers, telecommunications experts, and aviation officials understand that beauty may come with danger. The world becomes more interconnected each year. Vulnerability spreads along with progress. As our civilization becomes more technological, we also become more dependent on a calm magnetic relationship with the sun. Space weather has quietly become a field of national security, financial risk management, and international cooperation. On a more philosophical level, magnetic fields provide a comforting reminder that forces we cannot see still shape and protect our lives. We walk under the sky unaware of the invisible structures shielding us from dangerous radiation. Migratory animals navigate using Earth's magnetic signature. Our compasses point north because heated metal deep below our feet is constantly in motion. The auroras above polar regions serve as a visual signature of that protection, a reminder that Earth is a living, magnetic planet. Looking ahead, scientists are developing strategies to build artificial magnetic shields. For example, future Mars missions might deploy magnetic field generators to create mini magnetospheres to protect habitats from radiation. Some engineers have proposed placing a large magnetic shield between Mars and the Sun near the L1 Lagrange point to gradually help the planet regain atmospheric pressure. These ideas sound futuristic now, but they represent a new phase in human evolution, learning to shape magnetic environments to support life beyond Earth. We often say space is harsh, but that harshness is not random. It is guided by magnetic energy. The sun's magnetic field ties every object in the solar system into one connected system, like beads on an invisible thread. When something disturbs one part of that thread, a solar eruption here, a shift in solar wind there, the whole system responds. Planets adjust their magnetospheres, satellites withstand radiation, auroras bloom. Space weather is not case. It is cosmic communication. By listening more closely to this communication, we will gain the knowledge needed to venture farther into space with confidence. We will learn to anticipate the sun's storms, shield our explorers, and perhaps one day terraform worlds that currently seem hostile. The story of magnetic fields is ultimately a story of adaptation, how life and technology respond to the invisible winds of the cosmos. In the end, what makes magnetic fields and space weather so captivating is their dual nature. They are both destructive and protective, chaotic and structured, majestic and dangerous. They govern the birth of stars and the survival of planets. They light up our skies and challenge our ingenuity. To understand them is to understand the dynamic heart of the universe. And as our star continues to blaze, twist, flare, and evolve, we will continue to study its ever-changing magnetic ballet, not just out of curiosity, but out of necessity. For in that dance lies the future of humanity's expansion into space. From the dazzling glow of auroras to the silent hum of power lines, from the deep metallic pulse within Earth's core to the swirling plasma far beyond Pluto, magnetic fields touch every corner of our existence. Space weather, once invisible and mysterious, is revealed as the living breath of the sun and the cosmic winds that roam the galaxy. The more we learn, the better we can protect what we have, and the braver we become in dreaming of what comes next among the stars.